nice to see that sometimes we can use the structure of the matrix to calculate the characteristic polynomial in much better and easier way. In this case, I'm going to show you that we can use the fact that some matrices are built as blocks, and we can use those blocks to calculate very easily the characteristic polynomial of the matrix. In this case, look on this matrix A. This matrix A, you can see that we have, I can imagine to myself two blocks. One block is right over here, and the other block is, maybe I'll do that. One block is, if it will tell me, oh my god, no, okay, it's too much. I don't know. One block is, okay, it's not working. One block is right over here. 1, minus 1, 1, and 1, and the other one is just these two. Now, if I want to calculate the characteristic polynomial, we are doing a minus lambda I and taking the determinant. Now, if I want to calculate the characteristic polynomial, I can look on this a minus lambda I is built from two blocks. One block is right over here, and the other one is just this, okay? This is B and C, let's call them. So B is all of this, and C is all of this. So B is this part, and C is just the 2 minus lambda. So I just showed you that A can minus lambda I can be structured as blocks. So now when I'm taking the determinant of this A minus lambda I is just the determinant of B times the determinant of C. Now think about it, how easier it is. Think about the determinant of C, it's just this is just one number. And the determinant of B is much easier compared to a 3-on-3 matrix, right? This is just 1 minus lambda times 1 minus lambda times minus 1 times minus 1, right? The determinant of 2 by 2. So the determinant of this is just the determinant of the blocks multiplied. So let's calculate the determinant of each block. So this is the determinant for B, right, as I did, and the determinant of C is just right away its number. So here it is, the characteristic polynomial is just the multiplication of the determinants of the blocks of A minus lambda I. So this is it. Here it is. This is the characteristic polynomial. Very nice way to look on a matrix in a case of blocks. Let's call it at least triangular blocks. I mean, at least the blocks are just like triangular. And because it won't work if everything is blocks, it just in this case, and it must be that the blocks are at least constructing a triangular matrix, right? I mean, maybe you won't understand me, but we at least need that the matrix, here it is. A matrix M is block triangular, is written this way or in that way. You need at least, and then you can just take the determinant of M upper by calculate the determinant on the diagonal and multiply them. So I just can ignore the C. But it won't work, for example, for M equals A, B, C, and D. Right? I mean, I want him to understand me. This won't work. The determinant is not generally this correct. The simple property determinant is not true. Here is the correct formula. This is the determinant of A times this. So it's not very easy. You need at least a triangular form, upper triangular block triangular, in order to be very nice. The determinant of the blocks on the diagonal, upper triangular or lower triangular, it still works. Of course, a block diagonal, of course, but not if there are 4 blocks like this. It won't work very nicely because this is much worse. So thank you very much. This was on how we can calculate much easier the characteristic polynomial of a matrix using the structure by blocks, at least triangular block block triangular matrix. Thank you very much. If there are any mistakes or corrections, please tell me. And thanks for Gemini for writing it down. And thank you all. And that's it. That's it.